So, I welcome you all in today's lecture. It will be the final lecture on the introduction of this course. And if you remember, we were discussing different types of nonlinearities in last lecture. So, we had already discussed what is meant by geometric nonlinearity and what is meant by material nonlinearity. So, today we are going to look into two more kinds of nonlinearities which are present in any system, nonlinear system. The first one is force nonlinearity and the other is the contact or the boundary nonlinearity. And after this we are going to discuss several examples and so today we start with this force nonlinearity. So, what is force nonlinearity? So, force nonlinearity occurs when the applied forces depend on the deformation. Okay? As you can see here, the first point, the applied forces, the external forces will actually depend on the deformation of the continuum or the body. So, as the body deforms, the applied forces, the effect of the applied forces, externally applied forces will change. Okay? So, now you have to remember that force is a vector quantity. So, it has a magnitude as well as it has a direction. So, in many cases it might happen that the magnitude of the force remains constant, but the direction of the force changes according to the deformation of the body. Okay? So, you would guess that force nonlinearity is often accompanied by geometric nonlinearity. It is because of geometric nonlinearity, the initial and the final configuration, they are very different from each other. So, the shape of the body changes. So, the effect of the external force which are dependent on the deformation also changes. Okay? So, this fourth point is what we say, that the magnitude of force may remain constant, but the direction of the application of force may change. Okay? So, we will look into some examples. The first example is the deployment of a airbag. So, you all would have seen that in your car, okay, there is a airbag which is present. Okay. So, what is the purpose of an airbag? So, when the vehicle is impacted, okay, so it may happen that somebody is driving a vehicle and the vehicle gets impacted against another vehicle or against some rigid obstacle or any other reason. So, the purpose of the airbag is to deploy quickly enough so that it can protect the life of the passenger. Okay. So, when this airbag gets deployed, okay, so the air is blown inside the airbag and it expands. Okay. So, the pressure load inside the airbag will depend on the shape of the airbag. Okay. That is first example. Another example is the deployment of a parachute. Okay. So, when somebody jumps from an airplane and the parachute is deployed. Okay. So, you would have seen that the parachute is initially a very compressed inside a bag. Okay. So, when somebody jumps out of the airplane and he pulls off a lever, so the strings go out and the parachute is deployed. Okay. And it expands and becomes a huge structure. So, there also the shape, the effect of the air pressure on the inner surfaces of the parachute has an effect. Okay. So, when you are designing a parachute, you have to take this kind of force nonlinearity into account. So, another example is your contact problems. Okay. So, in the last class I have shown you a simulation of a contact problem. You had a small block, it was kept pressed against a bigger block and it was dragged along the surface of the block, okay, bottom block. So, you would have seen that the contact boundary for the top block was always constant, okay, but for the lower block the contact boundary changed according to time. Okay. So, the contact boundary was changing, hence these contact forces also change. Okay. On the lower block the contact forces will change. A part of a surface which is in contact for a certain amount of time, after certain amount of time, when the upper block has passed away, the contact forces will become 0 and the non-zero contact forces will occur at some other point. Okay. So, these are few examples of force nonlinearity. Okay. Now, coming to the example. Okay. So, we will start off with a very simple example of a cantilever which is under the action of a uniformly distributed load. Okay. So, as you can see here, you have a cantilever beam. Okay. It is fixed on the left hand side, and on the top surface you have a uniformly distributed load which is acting over the entire surface. Okay. Now, depending on the type of this load, there can be two cases. Okay. And we can classify the loads according to the way they act on the surface. So, the first case is you have what is called the dead load. Okay. So, as you can see, the direction, in case you have dead loads, the direction of the forces, you can see here the direction of the forces, they are always in the same direction as they were in the undeformed configuration. Okay. So, neither the magnitude of the load has changed, nor has the direction of the forces has changed. Okay. Next, we come to see what are called the follower loads. Okay. Why the name follower? You can see from this picture over here. Okay. As you can see, this load over here, okay, you can see here, the direction, the magnitude of the force, for example, has remained constant, but you can see the direction of the force has changed. Okay. And this force always remains perpendicular to the surface on which it acts. Okay. So, in the first case, you would see initially the force was acting in the perpendicular direction, but later on it was not acting perpendicularly to the surface. In the second case, what is called the follower loads, you can see the load still acts perpendicular to the surface. So, these loads are called follower loads. Follower because the loads follow the deformation. Okay. So, these are two different kind of loads that we encounter usually. So, as you can guess, dead loads are very simple to incorporate in any computational finite element code. Okay. But follower loads, since they depend on the normal to the surface. Okay. So, this force over here, if we write F, it is a function of the normal to the surface at that point. Okay. So, where n, the normal to the surface, depend on the point. Okay. So, this x is the coordinate of the point on which the force acts. Okay. So, now you could guess that this force will have a corresponding stiffness coming into the stiffness. Okay. So, we will come to it later. Okay. So, incorporation of follower loads is a little challenging. Okay. Now, we will see some pictures of force nonlinearity, where force nonlinearity actually takes place. So, the first picture that you see here is a deployment of a car airbag. Okay. So, you can see, suppose there is an impact and this car airbag comes out of a small enclosure and just fills up the space. Okay. So, and the objective of anybody who is designing this car airbag has to be to protect the passenger, say the driver. So, usually this car airbag is present on the steering wheel of the car. Okay. So, when the car gets impacted, so this airbag has to be deployed, and it has to deploy in a manner that before the passenger head hits the steering wheel, this airbag should deploy, and instead of the passenger head striking the steering wheel, the passenger head should strike the airbag. Okay. And he should not have the impact of the full impact of the steering wheel, so that his life can be saved. Also, the airbag should not get deployed so fast that when it's in the total deployed situation, when the head of the passenger gets impacted, it should not get rebound, and then he may have, so that he does not suffer the injury to his or her neck. Okay. So, this design of an airbag is a very challenging process, and you can see the pressure that is being, the pressure of the air that is being blown inside this airbag is always normal. So, the surface, you can treat the surface as a very thin shell kind of structure. Okay. It is purely elastic. Okay. There is no material nonlinearity here, but there is a huge geometrical nonlinearity which is present, and also there is this force nonlinearity, because pressure always acts normal to the surface, and you can see that the surface changes over time. Okay. The next example that we consider is the deployment of a parachute. So, in this figure you see it is a simulation of a person who is jumping with a parachute, and now you can see as the parachutes get deployed. Okay. So, suddenly you see all of a sudden you have a very huge shape change which takes place, and if you are monitoring closely, you can see the wrinkles. Okay. So, the small wrinkles which are present at the edge of the parachute. Okay. So, for a realistic simulation of a parachute, okay, so that you can deploy, you can design a very good parachute. So, you have to take into consideration the force nonlinearity. Okay. The next example that we consider is the contact. Okay. So, this problem is similar to what we discussed in the previous lecture. So, this is a problem where you have a block, okay, and on top of that block you have a ring. Okay. So, you have a ring here, okay. You have a ring here and you have a lower block. Okay. So, the Young's modulus and the Poisson's ratio, okay, for this ring, or as we call it here die, is 10 times as much as the Young's modulus of the slab, okay, or the lower block, we call it slab here. Okay. Now, what we do here is we press these die against the slab by applying a vertical force, and then keeping the vertical displacement fixed, we apply the horizontal displacement, so that the die gets dragged along the surface of the slab. Okay. So, in the first, so as you can see in the first simulation here, the die is pushed against the slab, and you can see really appreciable change in the deformation of the lower slab. Okay. The slab deforms a lot, and as you can see the contact boundary changes. So, initially there was a line contact, and as you applied the forces, the contact area changed. Okay. Now, once you have applied that, the second simulation shows the die getting dragged along the surface of the slab, and you can see here that the contact area of the die more or less remains constant during the simulation, while the contact area on the slab changes over time. Okay. So, initially you can see here, okay, I will run the simulation again. Yeah. So, initially you can see for the slab, initially the contact area was present on the lower left end. Okay. Next, at the end of the simulation, the contact area for the slab has shifted to the right hand side. Okay. So, the contact area is changing, and also the forces on the block are changing from time to time. So, this is a case of force nonlinearity. Okay. So, the next example that we consider is the cup drawing process. Okay. So, you can see here you have a blank. Okay. So, this is a blank which is pressed against the die, okay, and there is a blank holder, okay, which is putting a force on the blank to keep the blank in its position. Okay. So, it does not allow the blank to move vertically, it can allow the blank to move in the horizontal direction. Okay. And there is a die. Okay. So, the shape of the die is say cylinder. Okay. And then what you do is you have a punch and you apply a vertical displacement at a certain rate, so that this blank goes inside the die and takes the shape of a cylindrical cup. Okay. So, this somebody asks you to identify all the different kind of nonlinearities which are present in this particular problem. So, what are different kind of nonlinearities that are present? So, the first is the blank. Okay. So, the blank that you see here, this portion, okay, will go large plastic deformation, okay, and there will be a permanent shape change, okay, of the blank. So, this is nothing but material nonlinearity. Okay. The next is the geometry of this blank. Okay. So, initially the blank is a cylinder with a very small thickness. Okay. The radius is large, but the thickness is very small. Okay. So, but it is a plain blank. Okay. So, as you put the pressure of the punch, okay, as you push the punch downwards, the shape of this blank will change. Okay. And it will change drastically, so that from initially say a 2D surface or 2D blank, you will get a fully 3D cup. Okay. So, you have geometric nonlinearity which exists here. Okay. Now, apart from that, you have kinematic nonlinearity which is present between the blank and the other parts. For example, you have contact between the blank and the blank holder in this region. Okay. And as you push the punch downwards, the blank will come in contact with the die. Okay. So, this kind of shape you will get. Okay. You will get this kind of shape. So, you will have contact between the blank and the die, okay, at this portion. Okay. So, you will have kinematic nonlinearity which will exist between the blank and the other parts such as punch, die and the blank holder. Okay. So, between punch and the blank you will have contact, between the blank and the die you will have contact, and between blank and the blank holder you will have contact. So, this is a kind of contact problem where there is a contact between 4 different bodies. There is one body is blank, the other 3 are punch, the blank holder and the die. Okay. And the contact between the punch and the blank is the main driver of this process. So, what do you achieve once you do it, carry out this process? So, you get this kind of drawn cup. So, this is a finite element model, okay, final result from a finite element model of a blank which was initially of a cylindrical shape with very small thickness. At the end of the simulation you will get something like this. Okay. So, this is with purely isotropic material. Okay. Obviously, if you change material to anisotropic, you will get what is called wrinkling, but that is not part of this course. I will just wanted to show what kind of different nonlinearities which can come into this problem. Okay. The last example of we consider is a Taylor rod impact problem. So, I can see, as you can see here, a Taylor rod impact problem is used for dynamic material property characterization. So, what is Taylor rod impact problem? So, what you have here is a cylindrical rod, okay, of certain length and diameter, okay, and this cylindrical rod is impacted against a rigid surface. Okay. So, this rod may be made of a material that you want to characterize, and then what you do is you fire this rod against a rigid surface at a certain impact velocity. Okay. Now, so you remember, now we have shifted from static to dynamic problem. Here velocity is come into picture. So, here what are the different kind of nonlinearities which are present? The first kind of nonlinearity which is present is you will have plastic deformation of the cylindrical rod. There will be very severe plastic deformation which will occur in the cylindrical rod. As the rod impacts the rigid surface, see the impacted end. So, this end of the rod, what will happen? Initially you will have a radius of r0 and slowly it will mushroom out. Okay? It will mushroom out and then you will have large plastic deformation that will occur. You will have geometric nonlinearity because the initial shape of the rod and the final shape of the rod will be very different. So, you have to take into account geometric nonlinearity. Also there is contact between the rod and the rigid surface. So, there is contact nonlinearity which is present. Okay. And the other kind of physics that is present over here is if you impact the rod against the rigid surface at sufficiently high impact velocity, what will happen is you will see that the impacted end will fracture. Okay. You will see fracture of the specimen and you will get fragments. Okay. So, this kind of problems to simulate you have to take into account all kind of nonlinearities. So, here there are some finite element simulation results which I have shown, and these are the deformed configuration. Okay. And at two different impact velocities of 400 meter per second and 500 meter per second. And you can see the failure of the rod as it happens at different impact velocity. So, this black zones that you are seeing here are nothing but the failed elements. These are elements which have lost because of certain criteria, they have lost their load bearing capacity, and we can imagine that there is a crack that has come at these places. So, this is next level of complex problem where all different kind of nonlinearities will be present. So, from the previous problem where we had a static contact, this problem we apart from those 4 nonlinearities, we also have the fracture and then the dynamic effects that come into picture. So, these kind of problems are very computationally challenging. Okay. So, next we come to the characterization of nonlinear problems as either mildly nonlinear problems or rough nonlinear problems. So, what are mildly nonlinear problems? The mildly nonlinear problems are where the nonlinearity is continuous, okay, and there is a history independent nonlinear relation between the stresses and strain. Okay. So, the relation between stress and strain only depends on the current state and it does not depend on the history. Okay. If you have such a case, then there is a case for mildly nonlinear problem. So, you will have nonlinear elasticity, you will have geometric nonlinearity, and you also may have deformation dependent loads put into these kind of nonlinear problems. So, mildly nonlinear problems will have these kind of characteristic. Next comes the rough nonlinear problems. Okay. So, rough nonlinear problems will have all these characteristics, and on top of that you will have constraints. Okay. There are certain constraints which will be either equality constraints or inequality constraints on the constitutive relations. Okay. So, in the previous problem on the contact problem, you will see that there is a constraint that one body cannot penetrate inside the another body. Okay. So, this constraint has to be, when you are solving the system, this constraint has to be satisfied, and to satisfy these kind of constraints you have to devise certain kind of constraint handling algorithm which are taught as a part of computational contact mechanics course. So, here is just suffices to know that for roughly nonlinear problem you will have either equality or non-equality constraints coming into the picture. On top of that, you may have history dependent nonlinear relation between stresses and strain. Okay. So, history dependent means, for example, plasticity. So, plasticity problems you have the relation between stress and strain which not only depends on the current state, but also on the history of deformation. Okay. So, elastoplasticity problems and contact problems are classified into the roughly nonlinear problem. So, in this course we focus on the mildly nonlinear problems, and also we do not discuss the deformation dependent loads. Okay. So, we just concentrate ourselves into material nonlinearity and geometric nonlinearity. Okay. So, how are nonlinear problems actually solved? So, before we begin into seeing some examples of problems, that two simple problems we will solve. Okay. We should have a note on how nonlinear problems are actually solved. Okay. So, you establish the equilibrium between the external and the internal forces, whatever may be the problem, static or dynamic. You establish the equilibrium between the internal forces which are generated because you are applying external forces on the body, and then the body resists the deformation, and at a certain point of time there is a equilibrium which happens between the body and the external forces. Okay. So, for static problem, okay, problem where you can neglect the effect of inertia forces, you have following relation. The internal forces, okay, written here as F subscript int, and they are a function of displacement. Okay. So, internal forces usually depend on stresses, and stresses depend on strain, and strain depends on displacement. So, these internal forces are a function of displacements. So, these internal forces should be equal to the external forces, and these external forces may also have a dependency on the displacement of the body. For example, in follower loads you had that dependency. Okay. In case of dead loads, you only have external forces without any dependency on the displacement. Okay. So, in static problem, what you do is you try to balance the internal and the external forces. Okay. So, you can remember, connect this to your statics in your first year engineering mechanics. There also in statics, what you used to do was balance the internal and the external forces to get the reactions at, say, various joints. Okay. In dynamic problem, we have these two terms, the internal and the external forces which are already present, and we have an additional term of the inertia forces. Okay. So, inertia forces is mass into acceleration, u double dot. Okay. So, double dot denotes the double derivative in time of the displacement. Okay. So, in the nonlinear problem, you actually either balance the forces for static, in case of static problem, or you try to solve the Newton's second law for the dynamic problem. In case of usual your linear finite element, these equation boil down to Ku equal to F. This is what in usual introduction to linear finite element is taught. K is your stiffness matrix, U is the vector of your unknown displacement, and F is the external forces. Okay. So, for the static or the dynamic problem, these equations that you get are nonlinear equations. So, what you do, you have to solve these using some method which can solve nonlinear equations, and one of the most popular way to solve these nonlinear equations is through Newton-Raphson method. Okay. Okay. So, Newton-Raphson method is usually employed to solve this system of nonlinear equation which are shown here. Okay. How these equations come, we will see it in the course of our discussion. Okay. Later on, we will come across how you get these different force vector and what are the explicit expression for these force vectors. Okay. Now, again, the kinematic and the kinetic nonlinearities, they occur only on the boundary, okay, and they are handled by displacements and forces. Okay. So, if you have kinetic or the kinematic nonlinearities, they will usually occur on the boundary of the body, and they are handled by displacements and forces in the global sense. Okay. And you have to handle them explicitly. Okay. And these are very relatively easy to understand, and they are not very difficult to implement inside any code. Okay. On the other hand, the material and the geometric nonlinearity, they are usually present inside the entire domain. Okay. And they will depend on the stresses and strain. So, which means if they are present inside the entire domain, which means you have local effect. Okay. And to handle that, you have to have some implicit kind of strategy to solve the problem. Okay. which have these material and geometric nonlinearity. Okay. So, now we look into two different problems. Okay. So, some aspect of this nonlinear behavior we look through two examples. Okay. So, these two examples have finite displacements and they do not involve any material nonlinearity, neither they have force nonlinearity. Okay. So, they are only geometrically nonlinear problem. Okay. So, through these two problems we will show you some aspect of nonlinear behavior. So, the first example is bending of a cantilever beam. So, as you can see here in figure A, so you have a weightless rigid bar. Okay. So, you had a weightless rigid bar over here shown by this dotted line, okay, and you apply a force at the tip, okay, and there is a torsional spring present at the fixed end of the beam, hinged end of the beam, okay, or the bar. Okay. Now, as you apply the force F, the bar will rotate, okay, and it is a rigid bar. So, we neglect the deformation of the bar, okay, and the bar will rotate till an angle theta, at which point the equilibrium is achieved. Okay. Now, to derive the equilibrium equation, what you do is you have to get the free body diagram. First, you have to draw the free body diagram of the bar. So, figure B shows here the free body diagram of the bar. So, F on the right hand side is your external force, on the left hand side you will have a reaction force at the joint, and also this external force causes a clockwise moment, okay, to act on the hinged end of the bar. Okay. To overcome this moment, the torsion spring will apply a moment equal to k times theta, okay, where k is the torsional stiffness of the spring. So, the moment m applied by the spring will be k times theta. Now, so with this, using free body diagram and balance of moment, you will get the governing equation given by equation 1, okay, where moment m is equal to F into L into cos theta. Also, you can see that the torsion stiffness of the spring is k. So, the moment by the spring will be equal to k into theta. Now, the moment is balanced, okay, the moment due to the external forces given by equation 1 and the moment due to the torsional spring given by equation 2 should be balanced. This gives you k theta is equal to F L cos theta. Okay. So, this is the equilibrium equation or the governing equation. Okay. So, from this you get equation 3, which is a relation between the force F L by k. Okay. So, we assume that k and L are given to us. So, it acts like a scalar multiple to the force. So, this is the relation between the force and the cause of this, the effect of this force theta. Once you apply the force, you get theta. So, as you can see, there is a nonlinear relation which occurs between the force and the effect, which is theta, okay, because cos theta is a nonlinear term. So, there is a nonlinear relation. This equation, okay, you can see there is no material nonlinearity, there is no deformation, there is no contact, nothing like this, but still for this very simple case you have this nonlinear equation which comes into picture. Okay. Now, this is a nonlinear equation. Okay. So, as theta approaches 0, okay, say you apply a force which is very small, okay, is such that the deflection theta is very small. Okay. So, as this deflection approaches 0, what happens? The value of cos theta approaches 1. Okay. So, as theta approaches 0, cos theta approaches 1. This we already know. So, substituting these in equation 3, what we get is what we call the linearized equation. Okay. So, linearized equation means now our nonlinear equation has been changed from a nonlinear equation to a linear equation, and this equation will be F equal to K L by theta. So, this equation is a linear relation between force and the angle theta, okay, where K by L is a known quantity. Okay. You have been given K, you have been given L, and you know the value of K by L. Okay. So, this is like y equal to mx. Okay. So, therefore, this is a linear equation. Okay. Now, we can plot to further show the effect of nonlinearity. We just plot equation 3. Okay. So, this is the nonlinear equation, theta by cos theta equal to F L by K, and this is your linear equation, okay, which is given by equation 4, which is F equal to K L by theta. Okay. So, on the x axis we have theta, on the y axis we have F L by K. Okay. So, now we just plot F L by K with the value of theta. On the y axis we can change theta from 0 to say pi by 2. So, this vertical line over here, okay, this vertical dotted line is for theta equal to pi by 2. Okay. So, you can see the nonlinear equation how it behaves, and you can see this dotted line over here is the linear equation. So, you can see when the value of theta is very small, okay, on the lower left in this red box over here, okay, which I am pointing out right now, you can see the difference between the two curves when theta is very small, okay, is marginal. Okay. I mean, for values of theta which are less than 0.4, okay, you can see there is hardly any difference between the nonlinear curve and the linear curve. Okay. So, there is no difference, but as the value of theta increases, as theta becomes significant, you can clearly see there is a difference between the nonlinear curve and the linear curve. Okay. So, if you are trying to solve this problem, okay, say suppose you are given this problem and instead of using equation 3, you have used equation 4, okay, for the analysis, and if your theta becomes very large, what will happen? You will report a value of force. If you are using linear equation, you will report, okay. So, first I will rub this, okay. So, say theta equal to 1.4, okay. So, if you are using linear governing equation, you will report a value of force, let us say close to 2, okay. And if you are using nonlinear equation, you will have a value of force, say let us say equal to 9, okay. So, now a nonlinear governing equation will give you a solution 9, while a linear equation will give you a solution 2, and so you can see already there is a huge difference between the value of the forces. Okay. So, what this example shows is that you should be very careful when to use linear equations, okay, and when to use nonlinear equations. Okay. So, if your problem characteristic is such that you expect only small values of theta, so there is no point of going for nonlinear equation. You can just simply go with linear equations, okay, and you will remember from our last class that linear systems are always computationally faster, okay. You can achieve the solution faster. So, instead of going for nonlinear, you can get the solution using linear, same accurate solution using linear system, okay, linear equation. Okay. Next, we discuss our final problem, which is buckling of a column. Okay. So, this example is similar to the previous one, where we had the bar which was vertical, I mean horizontal. Now, we have a bar which is vertical. The torsion spring is already present, and now we apply a vertical force P here. Okay. There also we applied vertical force, here also we are applying a vertical force, and what will happen? Okay. So, this the column, So, we call this as a rigid column, it will rotate and then there will be a position at which the column will come in equilibrium with the external force P. Okay. So, to get the governing equation, what we need to do first is we need to draw the free body diagram. Okay. So, the figure B shows you the free body diagram. Okay. So, at the pin joint end you have a reaction force which will be equal to the applied external force P. Okay. So, you will have a reaction force equal to P, and at the fixed end there will be a moment because of this external force. Okay. There will be a clockwise moment because of this external force, and that moment will be P into this distance, say x, and this will be nothing but L sin theta. Okay. So, this distance is L sin theta. So, the moment because of this external force P will be P into L sin theta. Okay. And this moment will be resisted by the torsional spring which is present at the pin joint end, and this moment will be equal to K times of theta. K is the torsional stiffness. Okay. So, the reaction forces are equal. Okay. Now, balancing of the moment will give you this equation. Okay. K theta is PL sin theta. Okay. So, equation 1 is the moment, external moment because of the external forces, and second equation is basically your resisting moment because of the torsional spring. Okay. For equilibrium, the moment because of the spring should be equal to the moment because of the external forces, which is K theta should be equal to PL sin theta. Okay. So, now you can get a relation between the forces, external force P and the angle theta. Okay. So, just like in our first example where there was a nonlinear relation between the force and the angle, here also we have a nonlinear relation between the force and the angle. Okay. So, you can see here sin theta is a nonlinear function. So, theta by sin theta is a nonlinear function. So, there is a nonlinear relation between P and theta. Okay. So, here K and L are given to you and it is like a scalar multiple to P. Okay. So, this is a nonlinear equation. Okay. So, now there are two possible solutions to equation 3. Okay. So, two possible solutions to equation 3. The first one is theta equal to 0. Okay. So, if you have theta equal to 0, sin theta will be equal to 0. Okay. And then this means the moment m will be equal to 0. Okay. And with m equal to 0, equilibrium will be satisfied, but then this is what we call is a trivial solution. Okay. So, this is not much interest to us. The second is if you have a non-zero value of theta. So, then what happens? Then you have PL by K equal to theta by sin theta. Okay. That is your solution. And now we can plot this equation PL by K equal to theta sin theta. Okay. So, on the x axis you have theta and on the y axis you have the value PL by K, and then we can plot the nonlinear function PL by K equal to theta by sin theta, and you get the parabolic kind of curve. Okay. And this dotted vertical line, okay, this vertical line at theta equal to 0, which is dotted, is nothing but your first solution, which is theta equal to 0. Okay. So, these two solutions intersect at this point, okay, which is also called the bifurcation point. Why bifurcation point? Okay, because if you approach from the lower end, as you come to this point, at this point you have two different paths to solution. Okay. Either you can go this half or you can go this half. Okay. So, your solution bifurcates, that is why it is called bifurcation point. I do not discuss beyond this point here. Okay. Now, if value of PL by K is less than 1, okay, so which means if this is your line PL by K equal to 1. So, below this line, okay. So, below this line you only have one solution, which is theta equal to 0, okay. And now if PL by K is more than 1, which means on this side, okay. So, you have 3 possible solution. Why 3 possible solution? If you draw a vertical line, so you have one solution over here, you have one solution over here, and you have one solution over here, okay. So, now for a value of PL by K which is equal greater than 1, you have 3 possible solution which come into the picture, okay. So, next you can linearize. So, as theta approaches 0, what happens? Sin theta approaches theta, okay. And then you substitute this in this equation, okay, what you get? PL minus K into theta equal to 0, and one can recognize that this is a typical linear stability analysis where P equal to K by L is the critical buckling load for a column, okay. So, again for this equation over here you have 2 possible solution, one is theta equal to 0 and the other is PL by K equal to 1, okay. So, you see here, okay, you can see here this dotted line over here is PL by K equal to 1 and this is your line theta equal to 0, okay. So, for a linearized system you only have one solution, okay. This is that solution and that is your bifurcation point, okay. So, that after this point the column becomes unstable, okay. So, when applying to a beam column, such a geometric nonlinear analysis will yield you the Euler buckling load, okay. And this finite element context, the eigenvalues analysis, okay, will give you eigenvalues which will be nothing but the buckling loads, and the eigenvectors of that eigenvalue analysis will give you the buckling modes, okay. So, eigenvalues will give you the buckling loads and the eigenvectors will give you the buckling modes, okay. So, in both the examples that we have considered, we can get the solution only when you consider the nonlinear effects, okay. That is when you allow the finite displacement of the structure to happen. If you did not allow for the nonlinear displacement to happen, okay, nonlinear effects to come into the picture, you would not have got the solution, okay. So, with this final slide, I will end today's lecture, okay. So, remember there are 4 different kind of nonlinearities which are present into the system: geometric nonlinearity, material nonlinearity, force nonlinearity and boundary nonlinearity. Each of these nonlinearity has to be identified in a system, okay, and appropriate algorithms have to be devised or they have to be chosen. So, if you are writing your own code, you have to write an algorithm which can handle this kind of nonlinearity, or if you are using a software, you have to enable options which can take into account these nonlinearities. Remember that all these kind of nonlinearities are, some are difficult to solve, other are not that difficult to solve, but you need a significant amount of computational effort to solve these problems if nonlinearity is present. So, nonlinear codes can solve linear problems, okay. So, linear problem can be solved by a code which has the nonlinear capability, okay. But solving a linear problem using a nonlinear code, okay, would not be a wise choice, okay, because at the end you will spend a lot of computational effort which you could have avoided if you just knew that in my code there is no nonlinear effects, okay, and then you could simply use a linear code to get your solution very fast, okay. So, it is very essential that you know how to identify these 4 kind of nonlinearities. So, with this I end today's lecture, and in the next lecture we will start with the introduction to tensors and tensor calculus, okay. And I hope you have some idea about the nonlinearities. So, we will meet you in the next class. Thank you.